Yes, this plastic section modulus, since this is along, no, in the major axis, no, this in major axis, so z sub x, so kaning z sub x can be found in the table. This is the, I mean, since it still is 16, W16 by 31, wala dire, but in the next table, no, 16 by 31, this one, no, your kuan, ang imong kuan ana is this 131, your z, no, kaninga z for 31 is 54, no. So mo nang fy, because this the steel is A992, so fy is 50 ksi times 54, no, can be found in the table. So the value for the nominal strength, nominal moment, is 225 feet kilopounds. Then this is for your nominal, no, or plastic moment. Dapat, since this is the strength, design strength, no, allowable strength for the moment, dapat ang imong applied loads should not be greater than this plastic moment or nominal moment, no. So we compute the maximum bending moment through the total service dead load, no, and live load. So for the total service dead load, including the weight of the beam, no, including the weight of the beam is 31 pounds per foot. We have 450 plus 31, 481 pounds per foot. For a simply supported, uniformly loaded beam, the maximum bending moment occurs at midspan and is equal to M max is equal to 1/8 WL squared. Now you I believe, no, you know this one, no, already. For the simply supported beam nga uniform unloading, ang maximum moment dyan na is 1/8 times the uniform load times the whole length of the beam, no. This is for the maximum at the midspan, because ang tendency ani, the moment of that is, ang moment ana niya is ana na siya, no, I mean, deflection, the deflection is ana. So the moment of that, if try to, yes, no, na kabalo na mo ani to draw the shear moment diagram, then drawing the shear moment diagram, and also through equation, no, through equation you will find this value for the maximum moment at the midspan, no. Then compute now where W is the load in units of force per unit length and L is the span length. Then the dead load, the moment for dead load is 1/8 times 0.481 times 30 feet, because this is in kilopounds, so you have to divide this one by 1000, mo na nahimong 0.481 times the length of beam, which is 30 squared. Then for the live load, you have this M sub L is equal to 1/8 times 550 pound per foot, or 0.550 times the length of the beam, 30 squared. So the answer is 61.88 kilopounds. Then from this one, using the load combination that will give the critical value, or that will govern in the design, no, that will give the highest value, you have to use the 1.2 dead load plus 1.6 live load, or 1.2 in this case, this is moment, so 1.2 moment dead load plus 1.6 moment live load, no. The dead load is less than 8 times the live load, so load combination 2 controls, no. Kasagara, if dead load or live load lang given, this load combination number 2, 1.2 dead load plus 1.6 load will govern, no. So substituting these values, you'll get 164 kilopounds foot, or foot kilopounds. Then alternatively, or you can use this alternative procedure now to get the moment no? Factored moment. So alternatively, the loads can be factored at the outset, no? You can actually use the uniform load for 1.2 dead load plus 1.6 live load, but this WD and WL is your uniform load, no, for dead load and live load. So pwede ka actually and use the equation na 1.8 for the maximum moment at the midspan, 1.8 uniform load times the length of the beam. So for the uniform load, the answer is 1.457 times 30 squared. So that design strength, no, is equal to the resistance factor here is 0.9, di ba? 0.9. This one is, I think, discussed earlier. 0.9 ang where is design strength? No, 0.9 times this nominal moment. Nominal moment is solved earlier, which is 225 kilopounds-foot. So 0.9 times the nominal moment, or actually this is the plastic moment, no? 225. So kani siya dapat, this is actually your design moment or design strength. This is the allowable strength or design strength for LRFD, no? Dapat dili siya mo lapas, design, no? Design strength. So kani siya nga value, dapat this is the limit lang siya. So since this is greater than the moment caused by the factored loads, So, what is siya, the design moment is greater than factored moment. So, this section or this kind of steel W16P31 is satisfactory. For ASD, actually, the same naman yun siya. No, the same computation, the same procedure. It's just that, ang imong kuan ani, imong applied loads or your load combination for ASD, remember, is just the sum of your moment, dead load and live load. In this case, for the moment, yes, ASD load combination to control. So, dead load plus ilag ito ganina is 54.11 for dead load moment and 61.88. Now, so just sum up this one, you have the applied moment for the ESD 116 foot kilo-pounds. Alternatively, the loads can be added before the moment is computed. Yes, you can also like so in this procedure, no, the uniform load, which is 0.48 and 0.550, no, and use the as what we did no ganina for the LRFD. Then use this equation 1/8 uniform load L squared, no, equal to 116 foot kilo-pounds. For allowable moment, remember this one, for allowable moment is the nominal moment divided by the safety factor. For the ASD, you have 1.67 or 0.6 nominal moment. Nominal moment is computed, di ba, earlier, which is equal to 225 kilopounds foot, no? So, substitute, you have this 135 kilopounds foot, which is still greater than the computed due to the applied loads. Oh, yes, applied uniform loads, 116 ang answer. Less than siya, no? Meaning, this is okay, no? Good. So, allowable stress solution. For the allowable stress solution, you have the moment divided by the section modulus. This one, section modulus is for elastic section modulus, no? So, 116 times 12, this is for foot to inch, no? To convert to foot to inch or feet to inch. So, 116 times 12 divided by for this section modulus, for this type of steel, W16/31, the section modulus is 47.2. No, this can be found in the table. Now, gyapon. So, the allowable stress is, this is the applied stress, no? And the allowable stress is 0.6 times the nominal moment divided by the